When a constant source of EMF like a DC source is connected with a ohmic resistor, a steady current is instantaneously developed in the circuit during switching on and switching off. But when frequency dependent electrical components like inductor or capacitors or combinations of it in any form is connected with a DC source, the process is not instantaneous in the sense that a considerable period of time is taken for growth and decay of the current during switching on and switching off. Such a current which gradually grows and decays during switching on and off is called transient current, and the phenomenon of such kind are called transient phenomenon. Therefore, RL, RC, LC circuit when connected with DC source is discussed in a transient phenomenon which forms the basis of network analysis. Now Kirchhoff's law forms the basis of AC circuit analysis similar to that of your DC circuit, only that Kirchhoff's law is prefixed with the word complex. That is, complex current entering into a junction is equal to the complex current leaving the junction. Complex EMF is equal to the sum total of complex potential drop across all the components in a closed circuit. RL circuit, applying Kirchhoff's voltage law, we can write that E equal to IR plus L di by dt, where E equal to E0 sin omega t, and as we know in inductors, EMF is ahead of current, so therefore we can write I equal to I0 sin omega t minus theta, where theta is the phase difference between EMF and current. Now if your I equal to I0 sin omega t minus theta, you can always differentiate the current to get di by dt, which equal to I0 omega times cos omega t minus theta, which is equation 3. Now using this equation 3 and equation 2 in equation 1, we can rewrite the equation 1 as R I0 sin omega t minus theta plus omega L I0 times cos omega t minus theta, which equal to E0 sin omega t. Now we can expand the sin omega t minus theta and cos omega t minus theta using the sin A minus B and cos A minus B formula to rewrite the above expression as R I0 times sin omega t into cos theta minus cos omega t times sin theta plus omega L I0 times cos omega t cos theta plus sin omega t sin theta, which is equal to E0 sin omega t. Now we can rewrite this expression in a coefficient manner, that is coefficient of sin omega t and cos omega t manner, in the sense that R I0 cos theta plus omega L I0 sin theta into sin omega t plus within bracket omega L I0 cos theta minus R I0 sin theta times cos omega t, which equal to E0 sin omega t. Now we can compare the coefficient of sin omega t and cos omega t in the left hand and right hand side to write that R I0 cos theta plus omega L I0 sin theta is equal to E0 and omega L I0 cos theta minus R I0 sin theta is equal to 0, which are equation 4 and 5 respectively. Now we can square and add these equation 4 and 5 to rearrange and write the expression as R square I0 square plus L square omega square I0 square equal to E0 square, and this will give us the current I0, which equal to E0 by square root of R square plus omega square L square, which we can write as E mod by Z mod, where Z mod is equal to square root of R square plus omega square L square, and tan inverse is equal to omega L by R, which you can get from equation 5. Details of this current and the impedance expressions we can get directly from phasor analysis. VRVL represents the potential drops across the in-phase component and quadrature components. Inductive circuit, impedance lies in the first quadrant, so therefore the OA here represents the in-phase component, which is equal to IR, and the AB represents the quadrature component, which is equal to J times omega L, that is XL, which is the inductive impedance, and this can be written as Z cos theta equal to OA and AB equal to Z sin theta, and Z as such can be written as Z e to the power J theta. So therefore now we can directly write the Kirchhoff's voltage law looking to the diagram, that is E equal to IR plus J omega L into I being the potential drops. So therefore the I will be equal to E0 sin omega t upon R plus J omega L, where I can also be written as E by Z and Z being R plus J omega L. I equal to E0 sin omega t by Z e to the power J theta, which equal to E0 times e to the power J omega t by Z into e to the power J theta, which is equal to E0 by Z into e to the power J omega t minus theta. In a similar way, we can proceed for RC circuit, where we can write the Kirchhoff's voltage law as
Ri plus Q by C equal to E0 sin omega t.
We can rewrite this expression, that is R dq by dt plus Q by C equal to E0 sin omega t. And as we know, in a capacitive circuit, EMF lags behind the current, so therefore we can assume our current expression to be I equal to I0 sin omega t plus theta, where theta is the phase difference between EMF and current. Now dq by dt is equal to I, so therefore we can always integrate dq and substitute in place of dq, that is equal to I0 sin omega t plus theta dt, and integrate it to get that is equal to minus I0 by omega cos omega t plus theta. And using these two expressions 3 and 4 in one and rearranging, we can compare the coefficients also and rewrite the expression, that is R I0 cos theta plus I0 by omega c sin theta is equal to E0, and R I0 sin theta minus I0 by omega c cos theta is equal to 0. Now we can square and add these two expressions to get R square I0 square plus I0 by omega c whole square is equal to E0 square, and this will give us, that is I0 is equal to E0 by square root of R square plus 1 upon omega c whole square, which we can write that is E0 by R square plus xc square, that is equal to E0 by Z mod, where Z is the impedance and that can be written as R square plus xc square square root, and xc being the capacitive reactance. Here tan theta is equal to minus 1 upon R omega c, so therefore theta is equal to tan inverse of minus 1 by R omega c, which we can get directly from equation 6. Similarly, we can get also Phasor methods. Capacitive circuit lies in the fourth quadrant, as we know, so therefore our OB in the Phasor diagram represents the resultant impedance, and OA in phase component, which is equal to IR, AB being the quadrature component, which is the capacitive reactance, which can be written as minus J by omega c. So Z, which is OA plus AB, can be written equal to R plus minus J by omega c, which is equal to Z cos theta plus minus of J times Z sin theta equal to Z e to the power minus J theta. Kirchhoff's voltage law, E equal to IR plus minus J by omega c times I. So therefore I can be equal to current expression E0 sin omega t upon R minus J times 1 by omega c, which equal to E by Z, where your Z is equal to square root of R square plus 1 by omega c whole square, and theta is equal to tan inverse of minus 1 by R omega c. So therefore our current expression can also be written in a complex manner, that is I equal to E0 by Z times e to the power j omega t plus theta. Now exactly in the same manner we can proceed for LC circuit also, where we can write the voltage equations as L di by dt plus Q by C equal to E0 sin omega t, and since here the resultant can be either inductive or capacitive, we can assume to here is capacitive, and where if it is a capacitive circuit, then the current is ahead of the EMF, so therefore we can assume I equal to I0 sin omega t plus theta, which is the solution of our assumed equations. Exactly in the RC circuit case, we can get di by dt is equal to I0 omega cos omega t plus theta, and Q equal to minus I0 by omega cos omega t plus theta. Using these 3 and 4 equations, again in equation 1 here, we can rewrite and compare the coefficients, that omega L I0 times cos theta minus I0 by omega c cos theta is equal to 0, and I0 by omega c times sin theta minus omega L I0 sin theta is equal to E0, which is equation 5 and 6 respectively. We can square and add these 5 and 6 equations, which will give us E0 square equal to within bracket omega L I0 minus I0 by omega c whole square, and this will give us I0, which is equal to E0 by omega L minus 1 by omega c if it is inductive, or E0 by 1 upon omega c minus omega L if it is capacitive. Now Z here is the impedance, which is equal to square root of XL minus XC whole square, And here, if you see to the equation 5, omega is equal to 1 upon LC, as because cos theta cannot be 0. So therefore, the frequency which is equal to 1 by 2 pi square root of LC, this is called a resonant frequency, where the applied frequency is equal to the natural frequency of oscillations. Now, in the phasor analysis, we can write I0 is equal to E0 sin omega t by J times omega L minus 1 upon omega C, which is equal to E by Z, and Z is equal to square root of XL minus XC whole square. Here, your theta is equal to pi by 2 or minus pi by 2. If it is pi by 2 plus, then it is inductive circuit that lies in the first quadrant, and if it is theta is minus pi by 2, then it is capacitive circuit which lies in the fourth quadrant in the phasor diagrams. And our Z, which can be written as 0 plus or minus jz sin pi by 2. It is because our in phase component is 0 and quadrature component is z times sin pi by 2. It is the quadrature component only constitute the magnitudes of the difference of L and C. So therefore, we write z times sin plus or minus pi by 2 equal to e to the power plus or minus j pi by 2. So finally, we can write the current expression I equal to E0 sin omega t by Z e to the power plus or minus j pi by 2. That will give us equal to E0 times e to the power j omega t upon Z into e to the power plus or minus j pi by 2. Therefore, I finally equal to E0 by Z times e to the power j omega t plus or minus pi by 2. And here omega t plus pi by 2 when this circuit is capacitive. If it is inductive, then it is omega t minus pi by 2. Thank you.